Hi, this is going to be a short video for number 3, practice exam 2. Let's take a look at number 1, copper metal nitric acid, C lecture. This aqueous sodium bisulfate and aqueous sodium fluoride. Now we can do that here, sodium bisulfate and sodium fluoride. Okay, this is not metathesis because if we switch the ions here, it's just going to form the same thing. So here there's no reaction for metathesis or double replacement. So we'll check acid-base. So try Bronsted. When we do Bronsted, we'll inventory it. So we got sodium ions from both species. We have bisulfate, we have fluoride ions, and we have water. And then we consult the chart. Consulting the chart, we'll see that sodium ions are neither acid nor base. A bisulfate is both acid and base. Fluoride is only base. Water is both acid and base. And then we look for the strongest acid, bisulfate and water. Bisulfate by far is much stronger. And then we look for the strongest base. Bisulfate is negligible as a base. Fluoride is significant, water is not so. And so fluoride is going to be the strongest base present. And then we react the strongest acid, bisulfate, with the strongest base, fluoride. And we do this by transferring a proton over. And so sulfate will be what's left after we lose the proton on bisulfate, and we'll form hydrofluoric acid. All right, then we do this. We imagine this as being a competition between the forward reaction and the reverse reaction. So the acid here and the base here. If we go backwards, then sulfate is gaining the proton and hydrofluoric acid is losing the proton here. And so we are comparing bisulfate versus hydrofluoric acid. And here we'll need to use the chart for this. So I'll have to bring up the acid chart here next. And so let me bring that up here unless I already have it. No. So looking at this, bisulfate is fairly strong for weak acid, and hydrofluoric acid is moderate acid. So bisulfate is the stronger of the two. So this is going from stronger acid to weaker acid, and so this is our driving force. So we expect a reaction between these two, and the bases will follow because of the conjugate relationship. Yeah. All right. For number 3, lead 2 carbonate, and sulfuric acid, we did this in class, so C lecture. For number 4, let's take a look at that, and that's going to be show with arrows. I haven't talked about this much. The reaction between BF3 and NH3. This is going to be a Lewis acid-base reaction. BF3 is a pretty good Lewis acid. And the reason it's a pretty good Lewis acid is, if you recall, BF3 is an exception to the octet rule. BF3 has less than an octet. And so boron would like an octet, but it can't take the electrons from fluorine. That is, we can't form a double bond because the formal charges will be messed up. However, ammonia can come in here. And ammonia has a lone pair it can donate. And so the base is a lone pair donor, and the acid is a lone pair acceptor. And what we form is, we form something called a Lewis acid-base adduct, which is going to look something like this here. Where the lone pair now is a bonding pair. And both the bonding electrons in this bond here come from nitrogen. We have different names for that. This is called the coordinate covalent bond or dative bond. But this is the product here. So now boron has an octet. The only The situation here is this. Boron ends up with a negative formal charge, and nitrogen ends up with a positive formal charge. Normally we think nitrogen is more electronegative, so we'll be willing to donate electron density to boron. But in this case, the octet takes precedence over the formal charge. So this is not what we consider. We'd much prefer to have the nitrogen to have the negative formal charge and the boron to have the positive formal charge. But again, it doesn't work because of the octet. And so octet trumps this somewhat unstable formal charge arrangement here. All right, that's what I'm going to say about that. We have other examples of Lewis acid-base reactions, which I'll talk about in probably in another video here. Or maybe I'll talk about it here. Actually, let me talk about it. A topic, CO2. CO2 is also a Lewis acid, but when you look at CO2, CO2 has an octet already. And so it's unlike boron, it doesn't need more electrons. But CO2 can react with water. And this isn't necessarily the most stable thing, but the way it reacts is the lone pair attacks the carbon. And this makes sense because oxygen here is delta minus, carbon here is delta plus, so there's going to be a positive negative attraction there, but there's no room. Since there's no room here on carbon, because carbon cannot have more than an octet, it kicks these pi bonding electrons out, or these the double bonding electrons out, I should say. And what we end up with is something that's going to look like this. It's going to be, oops. It's going to be C, go with this here. We're going to have this water come on here. I'm going to flip the orientation of the water so that the hydrogen is over here like this. But you know what this is going to do is it's going to screw up the formal charges like over here. And so let's take a look at the formal charges that result from this. Get rid of the cursor. The formal charge on this oxygen is going to be positive. I like to circle the formal charges here, and the formal charge on this will be negative. Now, there's going to be something called the inductive effect. And the inductive effect is when I have a positive oxygen, this is hydronium-like. If you recall what hydronium looks like, as far as the Lewis structure goes, it's like this, where we do have a positive formal charge on that. And what that does is it makes the hydrogens here a lot more positive, that is, much more acid-like. And so that's the same thing here. This is going to be quite a bit more acidic here, this hydrogen, than in normal water. In normal water, we don't have a formal charge on there. Okay, the next thing that happens is what we call intramolecular, within the molecule. And so this is going to be an intramolecular acid-base reaction where we have this oxygen with negative charge, so it's like hydroxide, attacking this hydrogen here, which is like hydronium. So this is kind of like a hydroxide hydronium type reaction here. And what that's going to form is this. If that oxygen plucks off that hydrogen, that group there, we're going to end up with this, where that lone pair is now a bonding pair. And these electrons get left behind. So this oxygen plucks that hydrogen off and leaves these electrons behind. And that's what we call an intramolecular proton transfer, where the proton, the hydrogen plus, is transferred from one of the atoms to another. Oops, is that right? No, that's not right. Let's fix that. It should be a lone pair here. And then we have this. And if you look at the formula for this, this is H2CO3. This is carbonic acid. So what we have here is, actually, this is much more favored than the reverse direction. And so to show that, I'm going to write big arrows going backwards here. So if I had carbonic acid is going to want to decompose into CO2 and water here. But that doesn't mean all of it decomposes. It could be a little bit left over. It's a weak acid. The decomposition this is a Lewis acid-based type decomposition. But a little bit can react. So we have this back and forth, but definitely the downhill directions towards CO2 and water. And so this is just an example of a Lewis acid-base reaction here. And so two Lewis acid-base reactions, one with carbonic acid. So CO2 and water is acidic. It's going to lower the pH by forming a little bit of carbonic acid. All right, the last reaction here is glucose and potassium dichromate and hydrochloric acid. So glucose is C6H12O6. It's a sugar alcohol. It's a solid. And we're going to react that with, that's not glucose. I screwed that up. This is not glucose. All right, let me correct this. This is sucrose. Sucrose is made up of a glucose and a fructose. So let me fix that. This is glucose here. And so we're going to go with sucrose, C12H11O. Did I do 11? C12H22O11, sorry. C12H22O11. We double it, but we lose one oxygen, so we don't have to form that peroxide bond. So we got sucrose plus potassium dichromate, K2Cr2O7, plus hydrochloric acid. The sealed wet. So we could do a double replacement with this. Metathesis would yield dichromic acid, H2Cr2O7, dichromic acid plus potassium chloride. I had two of these. And we're going from stronger acid, hydrochloric, to weaker acid. But this we have to worry because when we look at this, dichromate is a strong oxidizer. And so there is potential for redox here. We have a strong oxidizer in the presence of acid. And then we look at sugar. Sugars are good reducers. Sugars are good fuels. So this is a reducer. And so what I would do is I would look at, I'd consult the chart here and I'd look for dichromate, which I'd find here. If I look for dichromate, it's right here. And then I just copy this reaction down. Dichromate plus 14 H pluses plus 6 electrons yields 2 chromium, 3 plus 7 waters. And it is a strong oxidizer. So, so I know that. This is what I'm going to have in the inventory. I'm going to have sucrose, sugar, solid, potassium ions. Potassium ions are extremely poor oxidizers. We're going to have dichromate. We're going to have H+. We're going to have chloride, and we're going to have water. And so we're going to try the chart method for redox method. And we're going to identify, potassium ions are an oxidizer. Dichromate and H+ together are an oxidizer. H+ alone is an oxidizer. Chloride is a reducer. And water is both an oxidizer and a reducer. And then we pick the strongest oxidizer. However, this is not on the chart. It's not on the chart, but it's a reducer. It's in other words, it's a fuel. You can burn the stuff. And so we know it's going to be a pretty decent reducer. And in terms of reducer, it's going to be much better than chloride and water. It's much easier to burn sugar than it is salt, like sodium chloride or water. And so this is for sure going to be our reducing agent. As far as our oxidizing agent goes, it's going to be dichromate and H+. That would be the strongest oxidizer. So if it's this, the oxidizer is easy because it's just dichromate. We just copy it off the chart, plus 14H plus however many electrons. Let's see how many electrons. It's going to go to chromium 3 plus 2 plus 7 H2O liquids. And so chromium's going from chromium 6, so this is going to be plus 6 electrons. So I recall. You don't really have to guess because it's here. Yeah, plus 6 electrons. I was looking at chromium 6 going to chromium 3, so that's plus 3, and we have 2 chromium, so it's plus 6. All right, now what to do about our reducing agent? So this is our oxidizing agent. This is the reduction half reaction. What we're going to do about our reducing agent is we're going to use the skeleton redox method. And we have to make an assumption. We're going to assume that it's completely oxidized to CO2 gas. And that's if we don't partially oxidize, we completely oxidize the sugar. And we can't oxidize it further than CO2 because it's maxed out at plus 4. And so we assume complete oxidation. Okay, once we do that, then we know the major products. So what we're going to do is we're just going to balance it. So I have 12 carbons here. I have 1 carbon here. So I balance it by changing the coefficient to 12 here. Now I have 12 carbons and 12 carbons. And then continuing on here, narrow the pen thickness here. I'm going to have 11 oxygens, and 12 times 2 is 24 oxygens. And so I'm going to need an additional 13, looks like, H2O plus 13 H2O. So that's 24 oxygens altogether. And then we balance out the hydrogens. So over here, I'm going to have 22 plus 13 is 45, 55. Is that right? No, 45, 30, 35, 35, 35. No, what am I doing? Hydrogens. I'm doing hydrogens. So I have 22 plus 2 times 13 is 26. 26 plus 22 is 48. So let me fix this. It should be 48 hydrogens. And then over here I have no hydrogens. So I need to do a plus 48 H plus 48 H plus. Okay, then we look at the charge here. The charge on the left is going to be 0. Sucrose is neutral, water is neutral. CO2 is neutral, but we got plus 48 over here. So I'm going to need to cancel those out with 48 electrons. So altogether, I'm going to have 1 sucrose, C12, H22, O11, plus 13 H2O liquids is going to produce 12 CO2s plus 48 H plus 48 electrons. 48 electrons, that's pretty electron rich. You know, if we can lose up to 48 electrons undergoing complete oxidation. All right, so what we'll do here is we're going to, I'm not going to cross multiply because this is going to result in too huge of a number. So what I'm going to do is, what is it, 48, 6 goes into 48 times. So I'm going to multiply the first reaction by 8 here, and that's going to give me 48 electrons and 48 electrons, and then it cancels out. So let's add it up. I'm going to get 8 dichromates plus 80, and then 8 times 4 is 32. Let's see, 8 times 14 is 112. I'm going to do it 112 H plus 48 electrons. Okay, that's the reactants here. Then I'll add the reactants over here. C12H22O11 solid plus 13 H2O liquids. Okay, that's the reactants there. And then the products, 8 times 2, 16 chromium 3 plus plus um, um, 56 H2O liquids is going to plus 12 12 CO2 plus 48 H plus 48 electrons. All right, let's try to simplify this. So over here I have 48 H plus, and then I have 112. So 112 minus 48 gives us 64 H plus. So I'll drop that down to 64. The 48 electrons cancel. I have 13 waters here and 56 waters here. So 13 is going to give me 43 waters left over. All right, so that's that. But actually, I should look at the driving force first before I get too far. So if there's no driving force, then we don't expect a reaction. So this is the oxidizer. This is the reducer. And then in the reverse direction, CO2 and H plus, this will be our oxidizer. It's gaining electrons going backwards. And then over here, this will be our reducer, because going backwards, it's losing electrons here. Then going backwards, this is gaining electrons here. So CO2 is going to be our oxidizer, and chromium 3 plus is going to be our reducer. And so let's compare the two oxidizers. Here, I don't think we need any chart, because CO2 versus dichromate. Dichromate for sure is a stronger oxidizer, and CO2 is not a very good oxidizer at all. That's going to be a weaker oxidizer. So we do have a driving force for this. And then overall, the net reaction is going to be 8 dichromates plus 64H plus C12H22O11 solid group sucrose is going to produce 16 chromium 3 plus 12 CO2 gas. That looks like it. Now, let's just make sure it's still balanced. So 8 times 2 is 16 chromium, 16 chromiums. 8 times 7 is 56 oxygens, plus 11 is 67 oxygens. Is that right? Over here, I only have 24 oxygens. I screwed up. Ooh, I screwed up because I forgot my waters here. So let's add the waters here. This is 43 H2O liquids. So 43 plus 24, 67 oxygens. So that works out. 64 hydrogens plus 22 is 86 hydrogens. And so 43 times 2 is 86 hydrogens. And so the atoms are balanced. Let's check the charge. Minus 16 plus 64 would be 38 plus 38. And so 16 times 3 is 30, 40. Oops, maybe the charge is screwed up. Let me check the charge again. So this is going to be minus 16 plus 64. It would be 48 plus 48. Plus 48 on this side, and then 16 times 3 is actually plus 48. So it checks out. And so we have a reaction here with the driving force going from stronger oxidizer, dichromate, to weaker oxidizer, CO2. So this is driving forces present. Okay, that's it for this video. I'll post another video later.